Welcome to this video. In this video I will be discussing on Holevo bound. So Holevo bound is a very fundamental bound relating to this quantum information, and it shows up in various places. It can be also related to data processing inequalities. These things I have data processing inequality I have discussed. So we will start with the discussion of Holevo bound and a related quantity accessible information, which I will shortly define. So the proof of the bound requires various small machineries that needs to be properly accounted for. So I will be dividing this proof into 2 or more videos. So there will be different kinds of parts or sections for this video, like there has already been for other videos. So we start with this setup where suppose Alice has some sort of an access to a random variable. So some event that she is observing, like a tossing of a coin or throwing of a dice, and with this she has some associated probability distribution, discrete probability distribution, and then she encodes the information about this variable in a quantum form. Essentially she prepares particular encodings in the form of quantum states, like whenever she observes head, she prepares one state, or if she observes tail, she prepares another state. Now once this encoding is performed, she supplies these quantum states to Bob. So we have Alice and Bob, and the game of Bob is Bob tries to decode. He tries to decode these states that has been supplied by Alice, because these states have some sort of a relation to this random variable that only Alice has access to. Bob tries to predict from these states what he can infer about the variable x. So there is some sort of a inference on Bob's part. So accessible information is a quantity which can be said as it is maximum over the mutual information or mutual entropy between the variable x that is there originally and the variable y that Bob will be inferring based on some sort of a measurement. So the point is this max that is there. So this is maximizing this mutual information over all the possible decoding strategies that Bob can have. So now we already know that data processing inequality, it tells that h of x is greater than equal to the mutual information between them, and the idea is that maximum mutual information can be exactly equal to the information associated with x. So the uncertainty associated with x before the measurement, or the information gained after the measurement. There are two ways to talk about this entropy of x. So the idea is it might be possible for Bob to infer the variable x exactly, and hence this mutual information can be at most equal to this. But this is not always the case, because in classical it can always be made to be exactly equal, such that there is a perfect encoding decoding procedure. But in quantum mechanics this equality is not achieved most of the times. We can get a understanding of that by looking at a particular intuition, by looking at a particular intuition. So the intuition that we can see is that in general, if we have two orthogonal non-orthogonal states, so psi phi, this is not equal to 0, then it is not possible to distinguish these states exactly. So basically, if we say that, suppose Alice, whenever she sees head with a probability px, she prepares this state, and with a probability 1 minus px, she prepares this state. And if they are not orthogonal, then possibly Bob cannot make a difference between or distinguish between these and this state exactly. So in this case, the intuition is that the information accessible to Bob must be definitely less than what is accessible to Alice. And if this is not the case, then what happens is that we say that, well, Bob can infer exactly this px and 1 minus px. That is same as saying that he can infer this state or this state exactly. Like he can make the difference. And then this means that Bob knows how to make the difference between two non-orthogonal states, and whenever he gets, suppose, psi state, he knows that it is not a phi state, and he can then prepare in his own laboratory, he can prepare this psi state, n copies of this state. So Bob distinguishes between this state and prepares n copies of this state. So these are copies, and hence the system that Bob has access to can be said to be like a cloning machine. But such a cloning machine does not exist quantum mechanically. It is an ideal cloning machine. We have to be careful about that, in the sense that it is exactly copying this psi state to an n copy. So quantum mechanics forbids ideal cloning, in the sense that you can have a cloning where the fidelity is almost close to this 1, but a cloning procedure of exactly 1 fidelity is not possible. So for two non-orthogonal state, and we can look at the proof of it. It is a small proof. So the proof essentially says that a universal copying machine will require a universal unitary to make such a copying transformation, but such a universal or global unitary is not possible. So suppose the intuition is you have a data slot in your copying machine, and you have a target slot. So this target slot is like the free pages that you have in your printer, and the data slot is like the slot where you insert the pages that you want to Xerox. So you put in now a state in this data slot, and then you switch on the printer, and inside you have to act with a global unitary u, and the final outcome that you expect or that you want is your blank page. So this is a blank page. So this blank page must become psi. So it has copied this to here. So the idea is, if copying machine works on two non-orthogonal states, psi and phi, they are different as well as non-orthogonal, then these two must be the cases. The blank page must get filled with psi also. It can get filled with phi also, using the same unitary that you have here, u. But then if this is the case, then you can simply take a dagger of this equation. So you can take an adjoint of this equation and multiply it to this particular thing. So you see here I have the adjoint of the second equation, and here I have the this part comes here, and the multiplication will give a square here because there are two quantities. And this side you just use the property of unitary, that u dagger u is identity. Then essentially you see that the inner product, which is a scalar quantity, must follow this particular equation here. But the only solution to this equation is 1 or 0. But you see, if it is 1, let's see. Okay, so it cannot be equal to 0 by this contradiction, because we will get a contradiction here. And it cannot be equal to 1 because that means that phi and psi will be same state because they are normalized. So there will be a contradiction here. But these two assumptions, so these two assumptions together gives us a contradiction that an ideal copying machine does not exist. So this means that intuitively Bob cannot distinguish between two non-orthogonal states, and hence he cannot get an access to this maximum possible information h of x. Now the Holevo bound, what it will do is that it will give a much more proper bound to this mutual information that is here. So this we will again look at the next video. So in this video I just laid down the formalism of this Holevo bound.